Okay, we have started the recording. Let's start. Good morning or good evening to all, and welcome to the data-driven community virtual meeting. My name is Ronen Arieli. I'm from Israel, working as a senior consultant in the field of data platform and architecture of enterprise-level systems. I am co-admin of the data-driven community, and I will be hosting the session today. A few words about the data-driven community. We are managing two branches of activity. The first is an annual conference called Future Data-Driven Summit. This year's conference will be held on September 2024. The call for speaker is already opened, but we did not announce it officially yet. We just opened it a few days ago. If you are familiar with a company that fit to sponsor the event, then you are more than welcome to connect them to one of the community leaders. Of course, the second branch of activity which we run is the weekly meeting of the Cloud Data-Driven User Group, like today. Today, it is not a lecture in a conference, but a meeting of a user group, meaning that we are more flexible. Please feel free to use the chat during the meeting for questions and discussions as well. You are also welcome to use reactions. It does not interfere with the course of the meeting. I love it a lot. If you hear something that you love, like, or you just want to clap hands, then feel free to do so. It is my pleasure to introduce our speaker for today, Ed Pollack. Ed is a renowned speaker and a leader in our community. In fact, I mentioned the Future Data-Driven Summit. Ed is one of the organizers of the yearly summit and will be with us this year as well. We are fortunate to have him share his knowledge with us today. Ed, you are welcome to share your screen and take control, maybe add some words about yourself.
All right, here we go. We're all ready to get started? Sounds great. Thank you very much for having me today. I'm a huge fan of free technical training, especially virtual, which is accessible to the whole world. So I'm glad to be here. Thanks. And thanks for hosting. This is a kind of a deep dive today into how analytic data is stored. I'm going to move quickly. I'm not going to cover every single detail, but I will share everything afterwards in case you'd like it. And if you have any questions, feel free to put in the chat. If it's big, giant, out of scope, something like that, we can chat about it later, no problem. I love diving into issues after the fact. So this is me. I'm a Microsoft Data Platform MVP. I've done a lot in the community. I've organized a lot of events, written, spoken, just done lots of things, and I enjoy this. Again, I love contributing to free technical training, whether it's in person or online, and I enjoy being a part of these events. I really do. We're here to talk about this, though, ultimately about a little bit of review, but really all about analytic data storage. And there's going to be an overarching theme of similarities. And that's really the key out of this whole thing. The details are details, but there's a lot of similarities to how analytic data is stored from platform to platform to platform. And once you begin to see those similarities, a lot of the details become similar. They seem familiar. And then we understand how we can write queries and load data and read data and so on and so forth in ways that are faster and more efficient. That's what this is really all about. And this whole agenda is all about. It's a lot of stuff, but it really is just one simple goal. And it's a fun one, honestly. It's a fun one to have because we can begin making smart decisions, even on platforms where we don't really know how things work. And that's very valuable. So quick review, we're here today to talk about analytic data. OLAP workloads. Transactional data tends to be involve transactions that have less rows, more of the CRUD operations, single row inserts, updates, deletes, merges, stuff like that. You'll tend to grab more columns and work with them. You know, if I want order information from an order I placed online, I want everything back. I want to know all the details. Tends to be very time sensitive, which is important. People are waiting. If I click on a thing in an app somewhere, tap on something, and I'm waiting, well, I'm waiting, and I don't want to wait long. If you have the patience of me, I know how impatient I am, then after a couple seconds of waiting on an app, I'm done. I kill it. I've moved on with life. That's just how I am, at least. I have no patience, and honestly, most users don't, and they shouldn't. Apps should be fast. And in general, not really aggregating a lot of data. And if we are, it's a small amount. The detailed data is very important, whereas we're not really going to be taking millions or billions of rows and crunching. It's just not really what we're here for. Analytic data, in many ways, is the opposite. We're taking lots and lots and lots of data, lots of rows, lots of files, lots of stuff, and we're crunching it. In general, those workloads tend to involve lots of inserts, usually bulk inserts or large loads of data at one time, or they're all staged coming in from edge devices or whatever. But in general, the data is coming in a very organized, predictable fashion. Could be some deletes, probably very few, if any, updates. In general, you work with less columns at a time, and they're often things that are aggregatable or analyzable in bulk, things like numbers and dates, and decimals, and stuff like that. In general, what we do with analytic data is not quite as time sensitive. People may still be waiting, but if you're generating some giant visualization or report or dashboard, you can wait a few seconds and no one's going to care. And you can also schedule a lot of your data loading, your transformation, your all those various things in the background to occur when it's convenient for you. And we aggregate a lot. That's important. We're going to do sums and mins and maxes, counts, standard deviations, and things like that. Those metrics are important. And they're going to be across a lot of data. And this second type of data, the analytic data, is what we're talking all about today. This really has nothing to do with the transactional world. It's really about the analytic world. And there are mixed workloads. This is not uncommon where you have mixed workloads. You have a transactional table with some analytic stuff on top of it, or vice versa. What I want to focus on really for the presentation when I say mixed workload are tables that look transactional-ish, but are really analytic. For example, log data is a great example. Log data can have lots of detail. You can have lots of rows, lots of columns, big stuff. But at the end of the day, you write it once and you probably don't touch it again. You may read it. Therefore, it's really there for an analysis. And therefore, we can treat it kind of like analytic data. History tables, Q tables, those scenarios, we have a giant thing and a little bit is current and all the rest historical. We could treat a lot of that like analytic data, historical data. And we can take the same conventions we use to speed up analytic data and apply it to that as well. In general, this is sort of data that is repetitive. The time sensitivity is very similar. You can still benefit from partitioning and V order, Z order, liquid clustering, things like that. Lots and lots of conventions available that we associate with analytic data, but we can also work here as well. In general, we don't really want to go mixing OLAP and OLTP too much, but these are scenarios where OLAP makes a lot of sense. And the best example is a data lake. A data lake is a mountain of data with lots of detail. It's naturally a mix of analytic and transactional stuff. Sorry about that. That should not happen. That's weird. I will close that immediately. Sorry. Anyway, we're going to start off talking about Columnstore indexes and SQL Server because there's something that's familiar to us. SQL is familiar to us. We understand it. And Columnstore, therefore, is easy to understand. And we can then transition from there into Parquet files, Delta Lake, and things like that. So Columnstore is the opposite in many ways of row store. I'm not really saying much there, but it's helpful just to start with that, in that you take your data, and instead of having row after row after row with each column one at a time, we separate our rows and we group them into row groups because you need to have some finite division of data. So you have some giant table with analytic data in it. It gets subdivided into what are called row groups, which can be up to 2 to 20th rows per row group. Then each column is stored separately in what's called segments. So each row group has a set of segments, one per column. So the total number of segments will be the number of columns times the number of row groups. A segment is individually compressed using its own compression methods, and it has only data for that one column. And it's important to note here that all this information, the data, the metadata, the row groups, segments, whatever, all that's just stored in MDFs and NDFs because it's SQL Server. All your data goes into data files, that's where it goes. And it's stored in 8 kilobyte pages. So even if you have petabytes of data, terabytes of data, end of the day, it's all being stored in 8 kilobyte pages. That's it. Just like everything else in SQL Server, it's not memory optimized. That's where it goes. And so how do we compress all of this? The real key about the compression with Columnstore, why I can compress really, really well, is that each segment is compressed separately, and a single column is a single data type. And it's going to have lots of repeated values. Even if they aren't that repeated, there'll be similarities that can compress really nicely. I'm going to mention this like 17 times during this presentation. Ordered data compresses more effectively than randomized data. And in general, even if you don't actively order your data, it will naturally order itself over time if you keep piling more onto the end, whether it's files or rows or whatever. You'll find that data, and this is like so much study goes into this. There's so much information and data on it. But in general, data that's close to other data is more similar and compresses better. And you can easily test that. You can say, hey, let me take some rows of data from my 2024 data set, January, compared to some other data from January 2024, and then take data from, I don't know, March of 2011. You'll find way more similarities in the newer data than the old one. Some will be the type of people that use your app, software releases, new data elements, whatever. But there'll be more similarities. That's important. And again, if any questions, feel free to put them in the chat. I'm not monitoring the chat, but Ronan is, and he'll stop me whenever it's convenient to answer questions if any come up.
One question, so if you already mentioned it, we are recording this, we said it in the beginning, and you don't need to ask, you can see the red circle at the top of the Teams application.
All right, cool. All right, so I'm going to talk about compression here and why it's really effective. And this is going to begin to repeat itself over time. So how do we take data and compress it, especially when we know all data types are the same? The first and simplest form of compression you can use is called bitpacking. It's what row compression, classic row compression is great at. And all it does is take away the excess unused bits from your values, whatever they are. Here's some examples here. We know that an integer is 8 bytes or 4 bytes, 32 bits, and they're fixed width, which means every single integer has the same number of bits normally. If we bitpack it, then suddenly we're only using the bits we need for the value. For example, 65,000 doesn't require 32 bits, it only requires 16 because an integer goes all the way up to like, what, 2 point whatever billion, and we're nowhere near that. The number 30 only requires 6 bits, it's just ones and zeros. Therefore, by simply taking numbers and removing all of the excess bits off of them, we can take and shrink the data. And the example here of just these numbers, I sliced the data almost down to a third of what it originally was using a very, very basic algorithm. So bit packing is a natural compression technique, and it's used in almost every analytic storage engine out there because it's so easy, it's very inexpensive, and it's very effective. On top of that, we could talk about many encoding algorithms. I'm not going to hit into every single one of them today. We're going to talk about the most common ones that go into compression. And the key to encoding is that it's lossless. Therefore, it's not like an MP3 where you lose a little bit of your resolution of the audio or whatever. With an encoding algorithm used in data, you're going to end up with the same data afterwards that you have before. All that it does is adjust how the data is represented in storage to make it more efficient. Some of the most common algorithms are dictionary, value, and bitmap encoding. And all the goal is just take repeated data and make it repeat less. And that's all it is. Save space, repeat data less, and then also, as a bonus, maybe make additional compression algorithms further down the line more efficient. So I'm going to talk about a few of these and show some examples of compression and how it looks. First one, and one of the simpler ones, is dictionary encoding. In practice, it's not really that simple, but it's easy to understand. And dictionary encoding says we're going to take repeated values that are big, and instead of repeating them over and over and over, we're going to create a dictionary, which is essentially just a hash table of reusable values. This is especially useful for strings or very large data types that consume a lot of space, and they have repetitive values. If you don't have any repeated values, dictionary encoding doesn't really help you at all. If you have a million values and they're all different, this provides no value. But if you have a million values and it's the same 10 things being repeated over and over and over, which honestly, many lookup tables and type tables and things like that, even just money, how often is the number 0 in there, for example, and it could be a huge decimal. It's very, very common. So what we do is we convert the values into dictionary lookups, And then that removes the need to have to keep repeating the big values over and over, which saves a lot of space. A note in SQL Server is that dictionaries have a maximum size of 16 megabytes. This rarely is an issue, but you may find that issue becomes a problem because if you hit that maximum size, then your row groups will get created undersized. You'll have more and more row groups than you should. But again, this is something that doesn't really happen very often. And the cause is usually very, very large, stringy data all over your analytic data. Here's an example of dictionary encoding. So let's say I have some values here. I love using desserts, cookies, things like that. I just enjoy that. I bake a lot. So here we go. Here's my database with some values for desserts. Then some get repeated over and over in the middle of a table. So I can see the values over on the left and the size in bytes on the right. I'm assuming varchar. If it was n varchar, it would be double. And so I can see I have a total of 203 bytes, the smallest one being 7 bytes, the largest one being 24 bytes. Nothing earth-shattering here. I create a lookup table now. Think of a dictionary as a lookup table, but it's done in the background and it's optimized, so it's all automatic. None of these algorithms are things you control. You can influence them. You can look at the metadata underneath them if you want to understand them, but it all happens in the background, and that's how it should be. You should not be manually compressing your own data. It should be automatic by an engine. So we have 5 distinct values here. That's it, 5 distinct values. And you can see the dictionary requires 82 bytes to store. And then our original data was 203 bytes. So the dictionary only requires 5 distinct values, and it's kind of small. Now that we have our lookup table, we can map it back to the original data and say, all right, I don't have to store these big long strings anymore. I can store these little index IDs instead. And that's really helpful. So instead of having chocolate chip cookies and blueberry scones, I have zeros, ones, twos, threes, and fours, and they can be bit packed, like all the numbers we're going to compress. And so the end result is that my dictionary encoded data requires only 33 bits. That's it. And my dictionary is about 4 bytes. My dictionary requires 82 bytes. So we're saying that my total compressed data here requires about 86 bytes compared to the 203 bytes of the original data set. And I've shrunk the data down to like almost a third of what it was originally. So by creating this hash table of sorts, mapping the data, I've shrunk the data down a lot. And this is a good thing. Smaller is better here. Smaller data means less reads, which means faster reads and less compute used to read the data. Cool. Dictionary encoding is straightforward. Value encoding is a little more complicated. I'll provide a few simplest examples here to show how it works. There are many other ways to do this that get very, very complex. SQL Server doesn't get too complex in the back end, but some algorithms can. The idea behind value encoding is to take numbers typically, or data types that can be represented as numbers, and manipulate them with math. Subtract, add, divide, multiply, whatever, to make the numbers smaller and more compressible. That's it. And we can use different rules for this per segment. Again, each segment is compressed separately, so we can use all different rules for each one. This can be combined with dictionary encoding. None of these encoding algorithms are mutually exclusive. You can use any or none when we compress data. So value encoding is all about mathematical manipulation of data. And I have 3 examples of it I'll show. Here's the first one. Let's say I've got a bunch of values, and you can look at them and say, hey, they're all divisible by 10. I can see how much space they take up right now in bits, bit packed. Let's say I were to take and divide all those numbers by 10. What would happen is I would go from a larger value to a smaller value that requires less bits. In this case here, 108 bits down to 76 bits. When we talk about, I see a question here about shrinking data down. In SQL Server, at least, when you shrink data in storage, on those pages, it stays compressed in memory as well, and it will not be decompressed until required by the storage engine. So if I take a 100 gig table and shrink it down to 10 gigs, and then I store it in storage that way, those compressed pages stay in memory for the purposes of use until they're read. And there's another point here about encoding is not encryption. That's very true, but it's part of how we shrink data down and make it smaller with any of the algorithms we're talking about here. True, sorry. Encryption is totally separate. If I said encryption, I apologize, but yeah. Anyway, you can see here we shrunk down from 108 bits down to 76. That's great. Here's a second example. We don't have to divide, we can subtract. Let's say we take the smallest value in a data set and subtract 30 from everything. We turn that smallest value into 0, and everything else shrinks a little. I can see here I didn't really save a lot of space. I went from 108 bits down to 101 bits. So for this kind of data here, dividing by 10 was more effective. Subtracting 30 was not very effective. And SQL Server can compute very, very quickly. And really any engine compressing data and encoding data can determine very, very fast using metadata what the right algorithms are to use. It's not going to take it minutes or hours. It'll take it, seconds, fractions of seconds to figure it out. Here's an example, though. We very often may anecdotally think that a large, chunky identity value with no repeated values doesn't compress well. Well, it may not dictionary encode well, but it can value encode well. Here's an example where I have 1.5 billion, and my identity is just marching forward. Well, what if I subtract 1.5 billion from all those values? I've now rebased it at 0. And so now instead of having 1.5 billion, 1.5 billion, 1, 2, 3, 4, and so on, now I have a scenario where I just go from 0 to 9. With 320 bits down to 46. That's it. Difference between compression and encoding, just to answer the question in the chat, it's a good question. Encoding is really a way of re-representing numbers to make them take up less space. Whereas typically compression is finding repeating patterns of bytes. So it's more logical, more storage-based to shrink it further. Encoding is very easy to look at and visualize, whereas compression can be very complicated and hard to visualize. These terms are very often interchanged, and I wouldn't really fault people for doing so, to be honest. It's not really a huge deal, but it's very these are all hand in hand used, and therefore I don't really like make a big deal about it personally. If I misspeak at all, don't hold it against me for the rest of my life. It's a very easy thing to do.
One point for everyone: if you use the chat for questions, don't delete it because we want to keep it for after the meeting as well. I saw that someone deleted the question that he asked me for it. Okay, so the chat is not recorded, so leave the chat as it is.
Cool. Let's march on forward and talk a little more about compression. Run length encoding is probably one of the most frequently used ways of summarizing data, shrinking it, and making it smaller. Run length encoding is used across the board by nearly every algorithm out there because, again, it's simple, it's straightforward, and it's easy. This basically just looks for repeated values and byte patterns and just summarizes. That's all. The easiest example is just using numbers. In practice, it'll take a look at byte patterns, which is way more complicated. You can't really do that anecdotally with your eyes, but this makes sense to us. So let's say I had some data and it repeats. For example, I have like the number 5 repeated 4 times, the number 4 repeated twice. I don't have to say 5, 5, 5, 5. I could store that as the number 5 with 4 repetitions, and that shrinks it down as well and is quite valuable. And the more data repeats and does this, the more you'll see your data shrinks down. So for example, here, my bit pack size on the left is 30 bits. If I simply summarize and put repetitions in, I shrink it down to 16 bits. There is a little bit of overhead storing the repetitions, but it's small. So for run length encoding, this algorithm benefits most from data that repeats sequentially. The more values repeat, the more patterns repeat, the better this does. And I'm going to mention this again, and I mentioned it a lot in the future, sorted data will compress better because sorted data will have the same values repeat over and over and over more often. So what is Columnstore compression like? There's 2 different algorithms that are proprietary. While Microsoft gives you a lot of insight into how they work, they don't give you all the details. There's white papers out there if you're bored that talk about them, that give you a lot of information, but they're not required to give you all the details, and they don't. So they use xVelocity for Columnstore and Express for Columnstore Archive. Columnstore Archive is simply a more aggressive compression algorithm. It gives you maybe an additional 20-25% depending on your data profile. But you do pay for it. It costs more to compress it. It costs more to decompress it in terms of CPU. But for colder data, that's great. You're not going to access it very often. If you're going to be updating it, that's great. Both algorithms will always use at least bit packing and run length encoding and try to. Others will be used situationally depending on your kind of data profile. Again, it's not going to use dictionary encoding if there's no benefit to it, or value encoding. It's only going to use it if it sees a measurable gain that's worth using it on. And this is something that's going to repeat later on. This confuses people sometimes at first, but there's a feature in Columnstore called Vertipaq optimization. And what this basically is talking about is the idea that within each row group, so we've taken our data, however many millions or billions or whatever rows we have, and we've chunked it into row groups. So each row group has up to 2 to 20th rows. You can have any number of them. There could be hundreds, thousands, millions. It doesn't matter. I've seen comps or nexts with hundreds of billions, trillions of rows. And you have a lot of row groups. Within each row group, though, the order doesn't matter. Columnstore doesn't care about order. Columnstore doesn't it's not like a clustered index where you give it key columns and it orders your data. In Columnstore, there's no prescribed order. And therefore, within each row group, order doesn't matter at all. It's compressed, but the order doesn't matter. So what Vertipaq optimization says that if order doesn't matter in each row group, we can at runtime, when we compress our data, reorder the data in some way that makes it more compressible. So when the segments are encoded, but before they're completely compressed and all those additional algorithms are applied, it's going to reorder the rows in whatever way makes it compress best. This is not a cheap process. It requires some compute to do it, but it makes your compression ratios get far better, and it makes your queries faster because of that. There's certain scenarios that can prevent it from working. They're kind of edge cases. If you run into them, you deal with them. But again, they're edge cases. I only mention them here because it's worth mentioning those details, but I'm not going to talk about this really here. But Vertipaq optimization is key in that when your data is ordered, you'll get even more out of it. But the key here is that you can reorder data at runtime and make it more efficient. And we're going to talk about this more later in Parquet land as well, and in Delta Lake land, because they have very, very shockingly similar algorithms to the same exact thing. Here's an example of Vertipaq optimization. We have all of our values on the left here, which aren't really in order. There's not a lot of repetition. And then on the right, we just simply take those values and reorder them. So now you have zeros, ones, twos, threes, fours in order. Do note that this doesn't shrink our data at all. Our data hasn't shrunk. It's the same size, 33 bits on the left, 33 bits on the right. That's it. But if I were to apply run length encoding, it would be more efficient now because now I have everything ordered and I have these nice little groups of values, one after the other, which is kind of nice. One key about Columnstore and about every type of analytic data store out there is that metadata is stored alongside the data, and the metadata is used for much more than like statistics are in row store tables. This metadata is extremely valuable. It helps us understand what kind of data is in there. In Columnstore, the metadata is accurate. It's not just a guess like stats. It provides things, the min and max and the count and so on for each row group, and then for each segment within there, if it's nullable or not. And so things like that are really valuable because, the engine can now make decisions about how to compress it, how to decompress it, how to read it and write it based on this information that can make things either faster. There's an idea called segment and row group elimination. We'll talk about it in a moment, and it's critical for this being fast. And data order is critical to this as well. I only mentioned a few of the dynamic management views here, but one nice thing about Columnstore is that a lot of how it works is exposed in views, and you can use those views. They're even well named. So if you want to dig in and understand how your Columnstore indexes work, you can dig into these views. There's many more out there as well, provide physical and logical information about them, and you can dig in and learn about how they work and use them. They're interesting. I'm not going to dive into demos here. There isn't time for that, but it's worth mentioning there's ways of seeing this metadata and understanding what it looks like, how it works. I've mentioned data order a few times. I'm going to mention it now in a more complete fashion and talk about it more for the rest of the session, really, on and off. Ordered data will always compress better than unordered data, always. And so you really want to order your data naturally by some filter if possible. It's very often in the world of analytics going to be a date or a date time. You may have some alternate columns that you tend to filter by or work with. But more often than not, your data is going to naturally order by a date or a date time. It could be an execution date, a sample date, a log date, whatever. You'll have some date or date time value, and that's going to be what you order your data on. And the nice thing about that is that if you just keep adding new data onto the end every day, every hour, every whatever, it'll kind of naturally order for you. You won't have to go back and rebuild the whole thing later. It'll be generally in an order, which is nice. Your order can be disrupted, of course. Maintenance, software releases, things like that can muck with your data order. Lots of updates and so on can mess with it. Therefore, rebuilding may have value. But in general, you don't need to do that if data is important and you already order by it. Of course, if your older data is inactive and you don't really touch it at all, it's read only, you're not going to go mucking with it again, it can be ordered once and left alone forever. In the SQL Server world, you can partition your data, and then the older partitions can be ignored, whereas the newer ones can be rebuilt, reorged, whatever. So the valuable in your table gets really big, partitioning. Always a good call out to make. And so ordered data is very, very important. And the Vertipaq optimization kind of underscores the fact that ordered data compresses better. What does this all allow us to do? It allows us to do two things. And this is really critical for why these things are fast, and it does not apply to row store indexes and row store tables the same way. There's two ways you can slice and dice your data, by column or by row. The first type of segment elimination we're going to talk about is by column. Let's say I have a table with any number of columns, 6 columns like this one, but it could be more. It could be an analytic table that has 50 columns, 100 columns. It doesn't matter. All the segments are stored separately. If I only query for certain columns, SQL Server is not going to read all the columns. It'll only read the ones that I ask for. So for example, here, if I ask for columns A and B, I get columns A and B back, and I ignore C through F. I don't read all those segments for C through F in memory. That's a lot of reads. You don't have to do that. They're all stored separately, right? Like batteries stored separately, right? So instead of reading 24 segments, I read 8. That's it. Done. Just query for the columns you need. You automatically will save on reads instantly. Now we can do the same sort of thing by row. Metadata within each row group tells us about mins and maxes and nullability and things like that. And that information can be used to determine, is there a range of values that you're querying for, and where is it stored? For example, let's say my data is ordered by date, date time, pretty well. And let's say I query for a very small date range that's only in one row group. SQL Server is going to know that because it knows the mins and maxes for each row group for each segment, and therefore can make decisions about that. And so let's say that I do that query, and all the values needed by data are only in row group 1. SQL Server is going to know that and ignore 2 through 4. This is a big deal. It relies on ordered data, but it means that you can query in a massive table with tons, billions of rows, trillions of rows, terabytes, whatever big data is to you, and it'll ignore most of it. That is key. It requires ordered data, but it's what makes things fast. It's one of the features that makes Columnstore fast. And if you rely on it, your data will be fast. If you don't, it won't be so fast. And of course, you combine a little bit of A and B, and you get this. Let's say that I query for a small date range across only 2 columns. I go from 24 segments down to 2. Imagine that it wasn't 24 segments. Imagine it was like 1 million segments or thousands of segments, massive amounts of data. If I can pinpoint data I need quickly and get what I need, it'll be fast. And that's very common too, right? You run quarterly reports, monthly reports, weekly reports. You do dashboards that do year over year, day over day, whatever. We very rarely say, give me everything. And even if we do, we're not going to mean everything. We'll need different chunks of data, certain columns, certain groupings of it. So we always have that ability to do so. And of course, writing has to be efficient too. Writing data has to be efficient. We can't simply read fast. We've got to write fast as well. And that's a big deal. When we write to Columnstore indexes, to run the reasons why when they were first released, there were these kind of garbagey read-only things that were hard to use because writing is very expensive. And we can't at runtime decompress, rewrite, and recompress lots and lots and lots of segments. You could, you'd be waiting a long time, and that waiting wouldn't be fun. So to facilitate faster writes, we have two structures that are added to make writes fast. One is the delta store, which is where trickle inserts go. If you trickle into a Columnstore index a few rows here and there, you're not going to go and decompress, recompress, and do all that. You're simply going to say, drop them into the delta store. These are just B-tree heaps, kind of heapish structures that store data temporarily. It's not going to store billions of rows. It'll store thousands. And then in the background, asynchronously, they get pushed into the Columnstore index when it's convenient. You don't have to worry about this. This is done automatically in the background, and it's convenient. When you read the data, it reads both sets of data to get what you need. But this is useful because it means you can trickle insert and not pay a huge write price. So there's a question here about ordered data. How does SQL Server know the data is ordered or not? It's done through that metadata. So that metadata tells us mins and maxes and so on and so forth. And it'll know for each row group whether or not a value is there based on those mins and maxes, which is the metadata. And again, keep in mind that in the row store world, with your standard clustered indexes and non-clustered indexes, the stats are estimates. There is no accurate metadata that tells you exactly what a table is going to have. That is a difference, and that helps us here. So SQL Server can automatically filter out based on metadata because the metadata is accurate. On the flip side, when I delete data from a Columnstore index, this is true in many analytic engines, it's not actually deleting. It's, again, going in and decompressing and deleting and recompressing at runtime is going to take a lot of resources to do. And so what SQL Server does is it creates objects called delete bitmaps whenever you delete data. And again, it's kind of a B-tree heapish structure. And it overlays your row groups and simply says which rows are deleted. And so when you delete rows, all it does is flag them in the bitmap. Done. So really, rows are soft deleted. This does get cleaned up later on. Reorg operations can go in after SQL Server 2019, and they will clean up deleted rows over time, so you don't keep them forever, wasting space. But deletes are soft deletes, and this is a good thing. Again, this is all in the background. You don't have to worry about it. It's automatic. But this is a good thing because it means you're not going to waste tons of compute writing to your tables, because deleting shouldn't be expensive. It should be fast, and this makes it really, really fast because you're flipping bits instead of deleting rows physically out of compressed stuff, which is expensive. So one more note on writing to Columnstore. Inserting lots of rows is good. Bulk inserts are good. Inserting lots of rows at once is good. You don't have to batch insert. I'll mention this in the Parquet world as well, and it's a best practice kind of later on. But when you insert data into Columnstore or into really any analytic data structure, you can insert lots of rows at once. You don't have to feel obligated to batch it in hundreds or thousands, which is a very common practice in the transactional world to avoid blocking. In the analytic world, you don't want to do that. Let's now jump into something completely different, but that isn't really completely different. It's a totally different format for storing data, but it's going to sound very familiar very fast. Apache Parquet. Parquet is used in a lot of places. It's used all over the place in Azure, and it's used all over the place elsewhere. And it's an open format. Open is a good thing here. Open means it's portable. That means you can bring in your Parquet files, you can use them, and then take them away with no vendor lock-in. That's a really nice thing. Not a lot of platforms offer that. Parquet does offer that. It's column-based storage with lots and lots of similarities to Columnstore. So I introduced Columnstore first because many of us have database backgrounds and we're familiar with how databases store data, so it feels a little more familiar. This will feel less familiar, except that it's going to basically be a very, it's going to copy a lot of what we talked about already, which is kind of nice. If you store data in other file formats that are not compressed or minimally compressed, things like JSONs and CSVs or whatever, it's going to be, this is much faster, much, much, much faster. It's column store data, but it really does a lot of the same things. So let's look here. I'm not going to really focus on the header and footer too much. What I really want to focus on are the row groups and the metadata. And so once again, we're talking about row groups. We have row groups here. Each row group is a chunk of data, and within each chunk of data are columns. And so the data for each column in a row group is referred to just as a column chunk. That chunk can be divided into pages. So a page is kind of the smallest unit of storage in the world of Parquet. And so you'll have a row group, you'll have column chunks, and you'll have pages with each one. You have one column chunk per column per row. So a row group here is a bunch of rows, just like in Columnstore. A column chunk is kind of like a segment, but you can have further subdivisions physically into pages. That's it. Row groups, column chunks, pages. Done. Very, very, very similar to Columnstore. Despite being a totally different format, a lot of the same conventions are followed. Metadata is also stored as well. So each Parquet file includes metadata about that file. What does it contain? It has information about the type of data stored in it. So we have an idea based on the metadata what's going to be in here. So I don't have to read the whole file to know what's in it. I can read the metadata. Again, very similar to Columnstore. And this metadata is accurate. It's not a guess, it's accurate. And so you'll have metadata for each column, for each row group. This is huge. And so this provides us the ability to read these files quickly and know what's inside of them. And yeah, they're stored kind of like Columnstore is stored. Very, very similar. A few notes. The metadata is separated from data, and it gives you some optimizations. It's not perfect, but it does provide some optimizations that you see in the Columnstore world. There's a default size. You may have asked, how big is a page? A default is about a meg in size. It can be customized if you'd like. It's up to you, but defaults are there for a reason. I wouldn't change them unless you have a reason to do so. Maybe you have very, very large values, perhaps, that maybe makes sense to have larger pages. But again, that's something that you would do. Data types tend to get extrapolated automatically, so you don't do anything, but in the back end, it's going to take your data types and it's going to put them in the simplest physical data type possible. You know, dates become numbers, strings become binary byte arrays. You don't have to worry about this. It does it automatically. And the minimum unit of reads is just the column chunk. So it's going to read at least a column chunk at any one time, which is a segment, right? So your minimum unit of read here is like a segment in the Columnstore world. There is a question here. Sorry, I'm taking all your fun away. Sorry. How can you read a Parquet file to examine it and validate its data? You can examine a text file using Notepad. You'd read it using an app. Can you physically try to look at it? Sure. But really, your ideal way to do it would not be to view it like a text file. The real ideal way would be to read it using an app. So whatever your app is that you're storing Parquet files for, whether it's Hive, whether it's Databricks, whether it's Fabric, whatever, wherever your Parquet files are parked, Parquet Park, sorry, bad jokes. Wherever they are, though, read it using that app. That's really the right way to do it. Validate data is correct. And data validation should be a part of any data load process anyway. So you always want to load data and validate. It's just a best practice in any system that you use. Just a good idea. How does it compress data? Well, there's some similarities and differences here. It supports a lot of algorithms and formats. You can go, a lot of proprietary systems like Azure and so on will just automatically compress using the algorithms that make sense. But you can specify algorithms if you want to, depending on what systems you're in. By default, it's going to use many familiar encoding methods to do what it needs to do. Run length encoding is de facto standard. Dictionary encoding, de facto standard. Bit packing, very, very common. Now, the cool thing about Parquet that's a little different from Columnstore is that the compression algorithms are applied at the page level. So not the segment, the column chunk level, but down to the page level. So you can have a single column chunk that has many pages, and each page could compress differently. That means that you have more compression algorithms, but it means your data can be compressed in different ways. And in general, that's a good thing. It means that they can be compressed more effectively because it's possible that in a single row group, you have a column chunk that has 4 pages in it. Each page can be compressed differently depending on the profile of data inside. So interesting here in that your column chunk is your minimum unit of read, but your pages can be compressed differently, which is kind of cool. All right. So up until now, we have talked about Parquet, and Parquet files are kind of like static structures. You write them, they store data, and that's it. You don't really play with them too much. You don't add data to them. You can. There's ways of doing it, but realistically, you write your files, and if you need to make changes, you rewrite your files from scratch, which is expensive sounding. If you have a lot of data, you can't simply go in and blow files away and replace them all the time. That gets really expensive. You may also want to have some transactional benefits too. Like I want to be able to read and write with concurrency. against my files, and Parquet doesn't really offer that. Parquet is a storage format. It's not a file system. It isn't a transactional world. It isn't an engine. It's just a storage format. It's an efficient storage format, but it's just a storage format. In Spark, I believe you want to specify compression types to use. You don't have to get detailed, though. You give it the algorithms, and it'll pick the encoding methods based on that. You can, and it depends on your implementation you're using, but when you choose the algorithms, you don't have to go into detail. You don't have to actually jump in and say, oh, I think we should dictionary encode this and value encode that. That's not how this works. You don't have to worry about that at all. But you can specify the overarching algorithm, and then it'll take it from there. Again, you never need to worry about the nitty-gritty details if you have a problem, but more often than not, those problems are rare, and they're kind of like edge cases. So I don't really worry, personally, in the world of analytic data, I don't worry about how it's stored, the nitty-gritty details, until I have an issue that concerns me, like why is my data so big, or why is it so slow is probably the more common thing. So let's dive into Delta for a bit. Delta encoding adds a whole layer on top of Parquet. The idea really is we need to deal with the fact that real life isn't just about writing files and leaving them alone. Very often we need to do additional things like have transactional benefits like ACID. You talk about SQL Server, whether you're in Columnstore or row store, you have the benefits of atomic, consistent, isolated, and durable transactions. That's a big deal. You might want that in the analytic data as well. Like if I decide to bring, if you have edge data pouring in some data lake, you might want to be able to read it at the same time. You don't want to be locked out of it all day. So therefore, you want some additional benefits. This is I have just totally dove into the wrong thing just now, and I apologize. Before I dive into Delta Lake, I wanted to mention Delta encoding. I just tripped myself up, and I deserve to be laughed at right now, and I apologize. We will talk about Delta Lake in exactly 2 slides. I did have one more encoding example of Delta encoding. I will put a big asterisk and put this in red here because I tripped myself up, which is awesome. You can really laugh at me right now. This is the benefits of a user group of being live, is that, things happen. We can laugh at them. Delta coding is a type of encoding available in Parquet, and it is not available in Columnstore. It's very different. And all it says is that I have values. Those values are consecutive or similar, and I can determine the delta between them and compress them efficiently. This example data here shows consecutive-ish values with very small deltas between them. I can simply say, give me the value, and then give me the deltas after that, and shrink my data. I'm not going to demo any more encoding algorithms today. This is the last one, but I wanted to mention it only because it can really shrink your data a lot. It's reminiscent of value encoding, and it's pretty useful. Now I want to dive into Delta Lake. I apologize for the confusion. It's recorded forever. Thank you, YouTube. Recorded forever. Delta Lake is a set of version Parquet files. It provides transaction log, it provides concurrency, it provides the ability to time travel and version your data. This sounds like a lot. It is a lot, but it can be very, very useful if you're reading and writing your data a lot. If you need people to have access to it like that, this can really help. It uses an optimistic snapshot isolation level to give ACID transaction capabilities, which again, you may want that. Do I want my data to be consistent or eventually consistent? And depending on what you do, you may want it to be consistent. It may be important that your reports are always accurate, that people can get to them, your dashboards, your analytics, whatever. It's important. It's important to note that Delta Lake consumes more storage, it requires more compute, and lots of updates will create fragmentation. It's a very similar challenge to Columnstore. You don't want to issue updates against analytic data unless you have to. The ideal workloads for anything analytic in nature will be those that are insert and read, maybe some deletes, but you don't want tons of updates. To do this, metadata gets stored in line with the data because you don't want to have some humongous central metadata source. There's centralized metadata, and there's inline metadata that provides more detail. And this is also an open source format. So Delta Lake is open source, just like Parquet. That's cool. No vendor lock-in, no worries. You can bring it anywhere you want. That's cool. So you can, and in Delta Lake at the end of the day, it's just a bunch of files. You have your Parquet files and a bunch of things on top of it. You can pick it up and take it anywhere you want. There's lots of components to it. I'm not going to spend too much time on the components, but I will mention them because it's worth mentioning them. Delta Lake is made up of a lot of things. It's worth mentioning because it's kind of complicated. There is a high level of complexity here, and it's the sort of stuff that you're not going to really dive into head first unless you need to. Your data files are Parquet files. This is just your data, your modified data, and stored in Parquet files. You have deletion vector files. Just like in Columnstore world, data is not really deleted, it's soft deleted. So when you delete rows, these files are created and maintained to tell you what data is deleted within your Parquet file so it can be ignored. They're stored as binary files. You have change data files that manage change data. So if data gets updated, deleted, emerged, these files will be created and used to illustrate change from point A to point B to point C to point D and so on and so forth. It's cumulative change. You also going to have delta log entries. This is just changes to tables. This lets you understand how tables change over time. We then have an additional component that isn't a part of Columnstore world, and that's checkpoints. And these aren't checkpoints in the traditional sense of backup checkpoints you issue in SQL Server. These checkpoints exist to allow a replay of actions, which means you can time travel and go back and forth and look at previous versions. So checkpoints give you a replay of actions, allowing you to take and say, I want to go back in time and see what my data looked like previously. And that's really useful. These can get big depending on how much you change. But again, people probably want this, and it's why it's here. And so checkpoints allow you to go back in time and see previous versions. And last but not least, I've mentioned the fact that this can get big. You can compact data and shrink it. In the world of Parquet, you can use optimize to shrink data into smaller size. It's especially useful after lots of deletes, lots of inserts, lots of updates, lots of operations. You can optimize and make things smaller. It's kind of like a reorg in the world of SQL Server, even not a rebuild, but a reorg. Let's do a comparison here quickly. It's worth comparing data and data formats and understanding them. Parquet by itself is great for data that you're going to store it and not rewrite it very often, not going to update it very often. That is what it's for, and it's really useful. It's great where concurrency isn't a huge issue because, again, there's no ACID transactions, no concurrency, and you don't need versioning. So Parquet is great when I want to store lots of data, and I'm just going to store it and use it. And I'm not going to be going back and making lots of changes. And when people read it, it's through organized processes. Delta Lake is great where you need more. You need transaction support, you need time travel, versioning, you need the ability to do lots and lots of streaming data, lots of inserts, updates, deletes, and contention may exist, right? You need transactions. So that's good for that. And one is not better than the other. But for certain applications, one might be more useful. Depending on your application, you may do one, the other, or both. And one nice thing is you can go from one to the other. You can go from Parquet to Delta Lake and say, you know what, I want to add those capabilities to my Parquet files. You can do that, and that's cool. Now we're going to begin talking about some more familiar things that stacked on top. I know we only have an hour, and I'm presenting a lot here. But now we get to talk about more similarities. Within Parquet files, these optimizations are not an open standard, but different implementations of Parquet and Delta Lake will use what's called view order optimization, which basically says, like we talked about Vertipaq optimization, within a Parquet file, the order of rows doesn't matter much. Therefore, it can reorder them in a way that compresses better. This is just like Vertipaq optimization. It's so similar. And it's available here as well in the world of Parquet. And the version files, though, when you order them, those are open source. So even though the algorithms for ordering them are kind of proprietary in nature, the v-ordered files remain open source, and you can use them as an open standard, which is kind of cool. And so Apache Spark has its own way of doing it. Fabric has its own way of doing it. Databricks, they all have their own ways of doing it. But it's the same basic format, same basic conventions. Now we'll get a little more complicated here. This is kind of like, I'll call this very, very roughly like a non-clustered index. So let's say you want to take your data and filter it by something that is not the ordering columns that you v-order optimized by. You can do what's called a z-order optimization. And all this is basically a co-location of data that allows to be searched faster when you have other columns that you want to order by. It does this by storing additional data and maintaining stats on it, and it is used to kind of balance your data so you can search by something else. For example, I may typically order all my data by date, but what if I come in one day and begin saying, I have to do searches by account, and account spans all the data? Well, I don't want to search all the data. And so I may add additional Z orders based on that column. So in Delta Lake, when there's a need to re-ingest incremental data loads, you reload a previous version before re-ingestion. So I guess you're asking, do I have to reload data that's already been loaded? What do I do? And it'll depend on the nature of your data load. If you simply loaded data via inserts and you want to get rid of it, delete, insert, do it again. If you're updating it, I would delete and insert. And I'll mention why shortly. But deletes and inserts are generally the way to go if you want to reload data in Columnstore world or in Parquet world as well, because fully deleted files go poof, whereas updated files can sit around for a bit. One last note, liquid clustering is something in Databricks. It sounds fancy and crazy. All it really is an optimization on top of Z-order optimization. It's used very similarly, and it is intended to be a way to more efficiently Z-order your data. So if you happen to be in a software version that allows it, use it. If you don't, you don't. All it really is Z-order optimization, but the methodology is faster and more efficient and more fluid, and what it does in the background to make it work is more variable. That's all. That way your predicate queries that may not be against ordered data can still be fast as long as you define liquid clustering on certain columns. So it's like Z-order optimization. It's kind of like a non-cluster index in the world of SQL Server. It does very similar things for you. Now, here's where it gets kind of cool. I talked about Columnstore, I talked about Parquet, and how similar they are. But what if you're using some proprietary software where you have no idea how it works because it's proprietary, right? If you're in Tableau or Snowflake or whatever, some other system, they may not tell you how their software works. They may not tell you how they store your data, but I can promise you that 90% of the conventions used here so far today we discussed are used there as well. I guarantee it's Columnstore. There's supplemental indexing, there's co-locating of data, there's encoding, there's compression, there's optimization of row order, V order, Z order, whatever. All these things are there. There'll be transactional guarantees based on things they add in that are kind of like Delta. They may even use Parquet under the covers or Delta or something like that, or a database. So you can bet and be correct that proprietary systems that are closed source use very, very similar algorithms. And that's very beneficial because that means we can make assumptions that'll help us write better code. Therefore, everything I've talked about today, everything can boil down into a few pages of best practices that help us make good decisions against analytic data stored anywhere. Anywhere. Number one, avoid updates. This is a huge deal. Don't issue updates against existing data unless you absolutely must. And if you do, consider ways to replace that with a delete and insert. It sounds nonsensical to delete and insert instead of update, but in a transactional system where asset operations are guaranteed, like Delta Lake or like Columnstore, it will be more efficient. And you have control of your data, so you can do that. Updates are computationally expensive because you can't simply go in and make all the changes separately. You've got to do them as part of a single operation. And that's super, super expensive. I can go into detail as why it's so expensive, but needless to say, it is very expensive. Next, when you load data, load it in order by whatever your most frequently queried column is. That makes the Vertipaq and view order optimization faster and facilitates better compression algorithms. Try to maintain it over time. If things you do muck up the data order, rebuild your data from scratch, keeping in mind that if older data is never touched, it's only the newer data to be mucked with, you can leave your older data alone, either in partitions in Columnstore or in separate Parquet files or wherever you happen to keep it. And if you have problems with your analytic data, you're not sure why it's working the way it's working, and you can't figure out why, use metadata to better understand what's going on. That's all. Just understand what we're doing. Metadata can really help us understand our data better. A little bit more here. In the SQL Server world, you can partition data, allowing you to take data and splice it off. There's similar capabilities in the Parquet world with how we z-order or v-order our data. You already have separate files though, so you don't have to worry quite as much about it. There are old school ways of partitioning data in Parquet and in Delta Lake. Partition has different meaning though. So partitioning makes sense in SQL Server. We won't do things like that all the time in the world of Parquet. If you have really big stringy data that's long, that's expensive, that is big, consider normalizing it. You may be able to save effort up front for the analytic engine downstream. Not all analytic engines do well with lots and lots of text data, especially when the cardinality is high, meaning it doesn't repeat very much. You may find the dictionaries fill up fast and don't compress efficiently. And dictionary encoding is available in many, many formats, and it will have the same challenge. If you have a stringy column that has millions of distinct values that are all huge, your dictionary is going to be strained under the weight of that. So consider normalizing data up front before you store it. You don't have to, but you may find that it speeds up and shrinks your analytic data. Only query the needed columns. This advice is true everywhere. Query the columns you need and nothing more. And if bulk insert functionality is available, use it. If inserting 1,000,000 rows at once is faster than inserting 1,000 rows at once, do it. And most systems have ways to bulk insert data so you don't row by row by row log everything. Updates don't do that though. If you do an update operation will never take advantage of bulk insert functionality anywhere. It just can't. The transactional nature of how you need to get your data from point A to point B ruins that. So consider this on any platform. If you have to trickle load data, that's fine, totally fine. But if you can insert more at once, do it. It'll make your life more efficient and faster. And those transaction logs will be smaller as well, whether they're in SQL Server or if they're in Delta Lake. So to kind of wrap up here, I wanted to give a little bit of time for questions. Knowing how analytic data is stored can really help us improve it. And I didn't go into the absolute most nitty-gritty possible here. I have other presentations on it if you're interested. But knowing how it's stored means that you can make good decisions about it. And because most analytic storage engines kind of do the same things, you can make similar decisions about how to store your data regardless of where it is. Even if you change platforms, you can start with conventions that are similar and then move forward from there and fine tune. Fine tuning is always what you do later. Generalized conventions you do up front. Pick the right tool for the job though. And once you pick the right tool for the job, follow the right conventions, whether it's analytic data or transactional data. If you can use open source data conventions, go for it. Migrating data from one platform to another is not cheap. Getting data out is not cheap. Getting data out of a database isn't too bad. Getting it out of Parquet isn't too bad. Delta Lake isn't too bad. But the more proprietary the format, the harder it is to store your data and get it back later if you need it. Just keep that in mind. That vendor lock-in is real, and it can hurt. With that, I know I presented a lot of information. I appreciate some of the questions along the way today. If you have any additional questions, now is a great time to ask them. You already asked all your questions. That's cool. Go ahead.
And if you want, you can also raise your hand and use the microphone if you feel that you need to express yourself in words. Great session, Ed. Let's give a few minutes for questions, even so you already answered a lot of the questions.
Happy to answer more now. If you think of questions later, feel free to hit me up elsewhere. I'm always happy to answer and address questions. I really do appreciate everything people are saying. Things right now. I appreciate it. Thank you. It's always nice.
You can use your camera. You can use your microphone. I will make sure that you can use camera as well in a second. 1 second. The microphone is available. You can ask your question.
Here's a question about. Oh, go ahead. Go ahead.
Hey, hi. Thanks for all the detailed explanations towards the data, the storage, and everything. I really appreciate that. With the usage of everything in cloud, in AWS world, it's like S3 is like one source wherein it's mother of everything. We just try to load data anytime for whatever needs. It could be smaller data, bigger data, Parquet data, cost management data. We store there. I would like to hear your thoughts using S3 storage versus the RDS, not the RDS, the Redshift in AWS, and then the Snowflake world wherein you have combination of features. How do you see your data storage? Where do you pick, and which one you pick for smaller data versus larger set of data?
It's a good question. I would say the larger your data gets, the more you want a de facto analytic platform for it. S3 is super cheap. It's great for just throwing files. It doesn't do anything really for you, but it's a great place to put data or really anything that you want stored as files. It's cheap, it's readily accessible, it's easy to get to from anything else in Amazon Web Services, which is great. If you want to run analytics against data, though, you want to put an analytic platform, whether it's Redshift or something else. You want an analytic platform for it. And so really the best place to put your data is the place that you can most effectively use it. So if you're storing small data, it may not need to be an analytic platform, but it can be. If you're going to be using it alongside other analytic data, you may as well throw it in there as well. Because honestly, convenience and accessibility of your data is very important. And trying to optimize storage and optimize everything as much as possible at the expense of usability isn't probably worth it. People are getting frustrated. So I highly recommend putting the data in the most convenient place to query it for whatever purposes you need, analytic in this case. And then if you need to fine tune later, fine tune. I'm always very adamant about saying that you should, store data in the most convenient way possible to start, the most correct way possible, but then fine tune later. You don't have to get in the nitty gritty until later. There are a few questions in the chat that I'll try to get to, and if I can't get to it all now, we can talk about them more later. For slowly changing dimensions, if you have a slowly changing dimension table, those by default, you update rows, right? You adjust the active dates, you add on more rows. They're kind of like temporal tables. I would still recommend delete and insert. I know it sounds silly, but from the perspective of the storage engine, whether it's SQL Server or Delta Lake, it will be a little faster. I know you're doing the same exact thing, but slowly changing dimension tables will create a lot of fragmentation in that regard. So you may find that a slowly changing dimension table may have to get rebuilt every so often. There could be value in partitioning the data, separating it, so the inactive rows are all over here and the active rows are here. I've done that before and found a lot of success in that, where I've seen slowly changing dimension tables that have they get big, they become large over time, and you take the stuff that's done, that has a start and end date, and you keep it all over here, highly compressed done data. Then your active rows, which is a smaller data set, go over here, and as they're completed, you throw them into here. So you would delete it from here, insert it into here, and then read the sum of the two of them. That's an optimization you can do anywhere in any storage system, and that could be a nice way to really save space, make things faster. But again, don't over-optimize, only optimize if you need to, and then go from there. And one more. Go ahead.
Before you move to the next one, I just want to inform everyone you can use your camera, and we will be able to see everyone sitting one near the other. So this is a good way to close the meeting afterward. So you're welcome to open camera, and we will continue with the.
Cool. Fun visualization. The last question I see here is a question similar to earlier about what software to use to view Parquet files. And I think the answer would be whatever the software is. And this is kind of a cop-out, and I apologize, but at least for me, it's true. Use whatever the software is that you're going to be using to analyze those files anyway, because you want to have apples to apples comparison. If you're using, for example, Databricks, if you're using Fabric, if you're using Synapse, if you're using Hive, Spark, whatever the places you're using to analyze your data, use that to view your files through that software, only because that guarantees that you're seeing what you intend to see. If I view my data over here using one piece of software, but I analyze using this piece of software, I could make a mistake. I could miss a column, I could miss a row, there could be differences, and I don't want those differences to be apparent. And so I would highly recommend simply using whatever the software is that you're going to use anyway. Use that for analyzing, for validating, for ensuring that your data is correct. And honestly, when you load any data on any platform, you want to have some data validation. People don't talk about it enough, but you always want validation. How many rows, mins, maxes, whatever, like very basic metrics can ensure that you loaded the right amount of data, and then day over day, hour over hour, minute over minute, whatever, when things go wrong. If I load 1 billion rows a day and I go down to 1 million one day, something's wrong. And so you can use validation as a way to help ensure that your data is correct as well. Let's see. I believe this video is being shared later on. Ronan knows the details of that, and we'll communicate that to everyone. And I will share the presentation afterwards with Ronan, and he'll share it with everyone as well. So if you'd like the slide deck, you can also have that as well. It prevents all of the fast typing and copying. Are there any additional questions?
I think that you went through all of them.
Awesome. Well, again, if anybody has any additional questions, feel free to find me, and we'll chat about them later. I'd be happy to.
Awesome. I want to thank our speaker, Ed, for a great session, and thanks you all for joining us today. You can follow me or Jen Joseph on social media to get update information regarding recording and the community in general. First, in any way you are welcome, and it's highly recommended to follow our community website. You can see the links on the chat at the beginning of the meeting. And we will see you next week. So just don't forget, follow us and join the next meeting. And
All
again,
right.
Session.
Thank you very much for having me today. I look forward to maybe being back in the future. Who knows? But thank you for hosting and for organizing these meetings. It's a lot of work and highly appreciated.
Okay, what do you mean, who knows? You already know that we need to start to organize the future data rooms.
Oh, I got to do work. I got to do work. Oh man, no, I'm kidding. But we're always busy organizing something, and it's a lot of fun. And this is great stuff for the community. It really is.
Okay, great. Thanks a lot, everyone. I will close the meeting at this time.
All right. Have a great night. Great afternoon.